Welcome back. In the first part of this lecture, we have seen some simple examples of how to define functions in Haskell, and especially how that differs from most contemporary languages. So we have seen that in Haskell, conditionals are expressions, not statements, but that Haskell programmers rather write guarded equations than conditional expressions. The other thing we have seen is how to define functions using pattern matching, and we have seen in particular how to define functions over lists using pattern matching. What we're going to look at now is how to define functions, because Haskell is a functional language, so we have to have a concise way to define functions, and that is lambda expressions. You probably know lambda expressions from the language that you're using. If you're a Java programmer, in Java 8, the lambda expressions were introduced. If you're a C# programmer, you know lambda expressions. If you're a Hack or a PHP programmer, you have lambda expressions. If you're JavaScript, you have lambda expressions. Lambda expressions are everywhere. C++, you name it, D, Swift. Every modern language has lambda expressions. And as we saw in the very first lecture, this was an invention from Alonzo Church in the 1930s. And most languages, lambda expressions look kind of similar, and in Haskell they look as follows. So they look like this: lambda x, arrow, body of the lambda expression. Now in the actual code that you type, you don't write a lambda. You write a slash, so you write /x, and instead of the arrow, you write a minus sign and greater than. But since we want these slides to look fancy, we're actually writing a lambda and a real arrow, okay? But when you write this in code, you write slash for the lambda, and you just write the arrow as you would expect, okay? So what is this thing? This is a function that takes an x and adds it to itself. And that function has no name, so it's an expression of function type. That's what lambda expressions are. They are expressions that denote functions. So in mathematics, and as Church designed them, or if you read the lambda calculus literature, they're written as a lambda, but we type them as backslash. And instead of the arrow symbol, we write the arrow symbol. Okay, but for the rest, Haskell, I think, is the language that is closest to the lambda calculus because it's based on pure functions. Whereas in other languages, lambda expressions are, I think a better way would be to call them closures. And we will see why, because they can close over variables in the outer scope. But these lambda expressions can have side effects. But as we said, it doesn't really matter. We are really emphasizing the fact that functional programming is programming using expressions. So why are lambda expressions useful? Well, they are useful because they allow you to express your intent better when you're querying functions. Let's look at this first example here. Instead of writing add xy equals x plus y, so this is a query definition, this is a function that takes a parameter x, returns a function that takes a parameter y, and then returns x plus y. Really, the intent is better expressed by this. Add is a function that takes a parameter x, returns a function that takes a parameter y, and then adds them together. Okay? So this is actually syntactic sugar for this. And when I write Haskell, I often write them in this form. Even though it's a little bit longer, it means that I have to type more characters, but I think this form is more readable than that form. And in the course of these lectures, we will switch between both of these. But again, if you look at my Haskell code, I prefer to write things using explicit lambdas to convey the actual meaning of a queried function. Lambda expressions are also useful when you want to make explicit that you're returning a function. That's in kind of some sense the same as querying, but here, like, if we define a constant function, so this is a function that given an a will return a function that whatever b you give it will return that a. So here it's defined const of x returns a function that will, whatever you give it, just ignore it and return x. Okay? So that constant function there is very concisely defined using a lambda expression, whereas here I think it's a little bit less clear. Const of x underscore equals x. So this one doesn't make explicit the fact that you're returning a function. So here it's also emphasized by putting the parentheses around the type, and here you don't do that. So this is how I would write this function. I would put the parentheses on the type, and I put the write the function as a lambda expression. Here's another use of using lambda expressions, and that's to avoid inventing names. Inventing names is one of the hardest things that we have to do with programming, and coming up with meaningful names. Because often, the language forces you to name something where you just don't want to name it, you just want to pass the thing directly. So, for example, if I want to map a function over a list, there's no reason I should give that function here a name f. And what does f say anyway? So instead, what I can do is I can just pass a lambda expression to the map, and that will be used to map this function over the list. All right? So this is not idiomatic Haskell. This is idiomatic Haskell. Really, the only place where you want to name something is when you use it more than once, or if it becomes clearer. But that's up to interpretation. Here's another oddity of Haskell, and that's called sections. So with sections, you can take a binary operator, an infix operator like plus, and use it as a function. So by putting parens around it, you can use plus as a function. So 1 plus 2 equals 3, and plus in parens, 1, 2, is also 3. Now this is a nice trick, because we can also put 1 or paren 1 plus, and we can do plus paren plus 2. So we can partially apply plus by putting parens around the plus. So here we see we can do 1 plus, which is a function that expects a second argument and will add 1 to it. And here we have the function, section, plus 2, which is a function that expects a value here and then adds it to it. So this is 1 plus 2 equals 3. So in general, if funny plus is a binary operator, then you can write plus in parens to use it as a normal function, and you can left or right section it by partially applying it to an argument. Okay? So this is something that you will see quite a lot in Haskell, especially here. If you want to have a function that increments something, you just write 1 plus as a section. So why are sections useful? Well, here are a couple of examples. You want a function that kind of takes an argument and halves it? Well, you just write open paren divided by 2. And you don't have to write lambda x divided by 2. So sectioning allows you to write something without inventing a name. And that's the whole goal of this exercise. Giving names is hard, so we want to avoid that, and sectioning allows you to do that. All right, so here's a preview of the exercises. The exercises will be available on the website. And in these exercises, we'll ask you to use some of these constructs that we have seen in this lecture to define functions. And as I promised you, this will be the last exercise that's very Haskell specific. But since, you know, we have been talking about how Haskell differs from other languages, I think it's quite useful to follow the rest of the lectures to do these exercises to get a little bit familiar with the Haskell syntax. And so happy hacking, and see you next week. Bye-bye.